Welcome to the course entitled Energy Efficiency in Buildings, which is especially aimed at highlighting the importance of improving efficiency in the consumption of energy, as well as developing the basic capacities to implement efficient systems in buildings. Energy efficiency ensures short-term profitability and is a strategic bet in the medium-long term as regards minimizing impacts on the environment from the building sector. The main objective of the present course is to develop basic abilities in the field of building analysis based on energy. Thus, the main techniques of energy efficiency that can be implemented in buildings will be explained, as well as the aspects of energy that can be incorporated as from the very first stage, that is, from the moment the architect starts to design the building. Finally, we aim to show how correct planning, before the architectural design, allows the incorporation of active solar systems suitable for use in air conditioning tasks. The concept map presented here shows the main tools available to maximize efficiency in the use of energy in buildings. These main aspects are design of the building according to the surroundings, taking into account the climate and geography, the use of natural techniques for the thermal conditioning of buildings, thus minimizing energy consumption. The remaining demand should be supplied, as far as possible, by active solar systems. To ensure that the building meets the requirements and that the overall design of the building is energy efficient, energy assessment is used as feedback for the design processes for continuous improvements in efficiency. Here, the importance of energy efficiency in buildings in Section 1 is detailed. The first question we might ask is, which are the key aspects to obtain energy-efficient buildings, both retrofitted and new constructions? The key aspects are all related to design. The design has to foster the natural techniques of thermal conditioning. Thus, the building's energy demand can be reduced to a considerable extent. Another key aspect is to design the building and the systems so the energy demand, which has been reduced by natural means, can be supplied as far as possible by active solar systems. To achieve this goal, coherent urban planning is necessary in order to maximize the global use of solar energy, avoiding shading from close-by buildings, fostering favorable wind currents, facilitating heat evacuation, etc. The objectives to be achieved with solar energy are as follows. First, to facilitate the use of natural and renewable resources in building HVAC, taking into account the components, building techniques, and the actual sitting of the building. Integration as another envelope element of active solar systems to produce heating and electricity. In the stage prior to constructing the building, the basic parameters to be taken into account are design, in order to maximize the energy efficiency and the use of both active and passive solar systems. The orientation of the building, so that solar gain can be maximized or minimized whenever required. For a better result, it is also necessary to take into account the sitting of the building. For any design that aims at maximizing the thermal conditioning of the building by natural means, it is necessary to bear in mind the surroundings, so that natural techniques of thermal conditioning can be adapted to the temperatures, winds, and radiation levels of the local area. It is also necessary to link the design to the surrounding vegetation and study its impact on the exterior and interior. To set the values of the different physical properties for the inside, the criterion is based on the demands of the final users of the building, so that comfortable conditions can be achieved. Finally, it is necessary to take into account the cost of the building and the integrated systems, as well as the profit one wishes to obtain thanks to energy saving. In Section 2, we explain the basics of the thermal conditioning of buildings. When designing the techniques of thermal conditioning, it is necessary to consider one of the main sources of energy gains of the building, that is, the sun. To assess the influence of the sun properly, we need in-depth studies of the radiation and solar path, in the figure, which to a large extent will condition the techniques suitable for use. For a simpler study of the sun's influence, radiation is divided into its main components, the direct solar, the diffuse solar, and the globosolar elements. It is also crucial to know the psychometrics of the area, including absolute, specific, and relative humidity, dew points, and wet bulb temperature. To improve the design and incorporate the influence of the psychometrics adequately, different tools are used, such as psychometric charts in the figure, which are widely used for such purposes. Other parameters that can be used are, first, the ground, thanks to its very stable temperature throughout the year. This can be seen in the figure. The ground can be used as a heat source or a heat sink. Second, the wind, which facilitates heat exchange. From these parameters, summarized in the diagram, we can calculate the energy balance for the building, and also calculate the thermal equilibrium. This equilibrium would be reached through the main heat transference mechanisms, conduction, radiation, and convection, as well as mass transfer mechanisms. The main heat sources are divided into external sources, that is, the sun and outside air, and internal sources, lighting, electric equipment, and so forth. The main heat sinks are the ground and the air in the exterior. If we study the sun as a heat source, we can say that the solar gain is caused by solar radiation. The total gain will be the sum of the solar gains of each single element and the ability of the building to conserve that energy. To a large extent, this capacity depends on the design, which should foster solar gain in cold areas and heat evacuation from hot areas. As mentioned before, the requirements and values of the variables of indoor conditions are set according to thermal comfort, and hence energy savings are linked to thermal comfort. To determine the relationship between the thermal conditions, the user and his or her subjective opinion, in order to establish the minimum comfort requirements, we use comfort indices. One of the ones most widely used is Fanger's PMV. One of the tools most used when designing buildings is the bioclimatic chart of Givoni on the screen. Section 3, following on with the basics of thermal conditioning, summarizes the main natural techniques for thermal conditioning in buildings. When first trying to maximize the natural techniques of thermal conditioning, one may wonder, how should we design a building for sharp changes in climate? To answer this question, the architecture of complexity is introduced. This architecture implements the techniques for heating and cooling at the same time, with insulation that avoids excessive gains or losses, but always ensures a minimum as regards ventilation. The main objective is to ensure comfortable conditions in both summer and winter. A dual design is required that will respond to different functions. As can be seen in the figure, one of the techniques that responds to this dual design is efficient shading, which prevents overheating in summer but allows solar radiation to enter the building during winter, in the figure. Apart from the passive techniques, which reduce the demand for electricity, it is also necessary to develop active designs employing renewable energies. To develop natural techniques for heating, the following concepts must be implemented. Preventive techniques to avoid heat losses, such as compact buildings, good insulation on glazed surfaces, double glazing, external shutters, avoidance of hot points, passive heating techniques to maximize solar gains to heat the inner spaces. In this sense, we have direct solar gains, for example windows, semi-direct gains, referring to damping spaces, indirect gains, referring to opaque walls. To employ natural techniques for cooling, it is necessary to develop the following concepts. Preventive techniques to avoid gains, such as non-compact buildings to increase heat evacuation, ventilated facades, walls with insulation and thermal inertia mass, outside shading, such as curtains, blinds, awnings, plant covers, and passive cooling techniques. This slide shows a summary of all the concepts addressed in this section. Simulation is one of the tools most widely used to help in the design process. Simulation is used as a previous theoretical energy study, representing a perfect complement to experimental studies. Section 4 introduces its basics. Simulation is a circular process with different stages, in which the different stages interact through feedback in order to achieve a close representation of the real system. These stages are the study of the real system, which allows us to obtain a model that will represent the mechanisms of heat transfer of the building. From this model, we develop the simulation program, which affords certain results. If the model and the simulation program are properly developed, the model is validated. By contrast, the model can be modified to obtain a closer representation of reality. To develop the simulation, the real system must be characterized. To this end, the system is described with a level of detail sufficient to represent its complexity, including its inner components, walls, windows, and so on. The surroundings are also detailed, since the climatic conditions, close-by obstacles, as well as other elements have a strong influence on the real system and must be taken into account when simulating. Once the system has been characterized properly, the model is presented as an abstract representation of reality, the boundaries and limits of the model being set from the very start. This process leads to the formulation of a physical model and affords a description of the mathematical function that characterizes the system. Simulation tools have several advantages that make them very suitable during the first stages of design. Thanks to them, it is possible to evaluate different scenarios for a given case. It is also possible to perform sensitive analysis of the different elements of the system without additional costs. Thus, it is possible to optimize the energy behavior of the system subject to fluctuations in the different parameters. Simulation is an excellent tool for architects and technicians, especially in the first stages of design. It allows them to foresee and evaluate, from the point of view of energy, the behavior of the system under different scenarios. Within the multiple classifications that can be made, simulation models can be divided into 3 groups: static, dynamic, and models of correlation. A very important stage in the overall process is energy assessment under real-life conditions. This will be addressed further in Section 5. The energy assessment of buildings through monitoring is very useful to gauge the comfort conditions of the building, thus ensuring that indoor requirements range between the accepted limits. Thanks to the monitoring process, we can obtain the most significant variables and constructive parameters, and hence compare them with theoretical studies. These data provide enough information to validate the theoretical models presented in the previous stages. Examples of the tools used in the monitoring process are shown in the figures. These elements are temperature and solar radiation sensors. We can finally conclude that after the design and construction of the building, monitoring provides an adequate evaluation of the energy saving achieved. From this evaluation, we can characterize the building and compare it with others. It is also very suitable to certify the building's quality and guarantee the proper operation of the construction, at the same time seeing the building's defects. Section 6 gathers the basics of the integration of active solar systems in buildings. The objective here is to study the different types of solar modules, and they are used to maintain comfortable conditions inside buildings. Another of the objectives is to determine the parameters that will ensure proper integration, such as orientation and tilt, so energy production can be maximized and costs are minimized. 3 of the main issues to be taken into account in the integration of active solar systems are aesthetics, design, and cost. To improve the working conditions and maximize energy generation, it is recommended to facilitate a simple assembly process that allows simple and inexpensive maintenance, so the nominal parameters will not differ very much from the ones calculated under operation conditions. Each solar system, as well as all buildings, must be studied individually. There are as many solutions as installations, although there are common rules of general application. There are different conditions and parameters that change from one building to another, and these have to be analyzed in each case. The most important ones are environmental conditions such as climate and solar accessibility, the building per se, integration with conventional systems. Let us have a look at each of these influential factors. The orientation and shape of the building strongly influences the installation of active solar systems, especially when such systems were not installed while the building was under construction. The three main structures are a flat roof, a pitched roof, integration on the facade. Flat roofs usually facilitate the mounting and maintenance of the systems, since they allow the orientation and tilt of the modules to be varied. Thanks to the shading projected by the modules, the roof can reduce the cooling load. On pitched roofs, the orientation and tilt of the collectors are limited by the structure of the roof. Aesthetic integration is normally fostered by this kind of structure. Indeed, in some cases traditional building materials can be replaced by the elements of the active system, thereby reducing costs. Regarding integration on facades, their inclination does not help integration, and so different solutions must be sought. Integration must always use the facade with the highest incidence of radiation: south-facing facades in the northern hemisphere, north-facing facades in the southern hemisphere. It is necessary to calculate the production of the modules in order to have prior knowledge of the feasibility of the installation. When possible, it is recommended to substitute conventional materials by the elements of the active solar system, as well as to use these elements to produce shade. In the upper left figure, we see the usual structure of a photovoltaic module. Different kinds of cells, with several colors and levels of transparency, are used to foster integration. Several examples are shown in the bottom right figure. In the field of solar thermal collectors, the main types are flat plate collectors with TIM, evacuated tube collectors, and CPC. This figure shows an example of a plate collector with its different components. The field of application of active solar systems is very broad, with important applications in industry as well as in other fields. The most usual thermal applications on buildings are domestic hot water with a working temperature of around 60 degrees Celsius, heating with temperatures ranging between 35 and 45 degrees Celsius, pool heating at around 26 degrees Celsius, solar cooling with the highest temperatures, that is, over 80 degrees Celsius. This table shows the main aspects to be taken into account before active solar systems are integrated. The design of the building must couple conventional systems with the active and passive solar systems. The integration must be economically feasible in order to be attractive to users. It is necessary to combine energy saving with the substitution of conventional materials, so that the internal rate of return will improve. Simple installations and easy maintenance are a must for the modules to be close to their production maximum. Thermal stress must be borne in mind. It is also necessary to consider the influence on interior comfort conditions. To end this presentation, here we show several examples of energy-efficient building designs. In this slide, we see one of the buildings that were constructed within the Bioclimatic and Solar Cooling Project, the RETROFIT project led by CIEMAT. This building is an excellent example of active solar system integration on the facade. Here we see another of the buildings that belongs to the RETROFIT project. Note the integration of photovoltaic modules on the plate glass and the use of the greenhouse effect as a passive heating technique. Finally, this last slide shows another building from the RETROFIT project. Active solar systems can be seen on the roof, with the double aim of also shading the building. These shadows benefit the building by protecting it from the strong radiation present in the area.